Hey, welcome back. So last time we looked at greedy algorithms, and we just basically talked about what is a greedy algorithm. And it was essentially just an algorithm where it says, okay, I need to make a choice right now. Well, I'm not going to care about any future implications. I'm just going to look at a rule or heuristic I'm using and say, okay, I'm going to follow this rule right now and make my choice based solely off that rule and not worry about, the implications later down the line. And we saw, well, okay, that's kind of an easy, simplistic way to look at a problem, and you're right, it totally is. But what I alluded to last time is there are actually problems that seem complex, seem difficult to solve, and there actually exists optimal greedy algorithms to solve it. And we, saw what an optimal greedy algorithm is last time. But let me give you two potential problems here. One is a very, very, very difficult to solve problem, kind of like you could say an open problem still. And one's actually a very, very easy to solve problem. In fact, it has a greedy algorithm solution to it that's optimal. And on the surface, it's not obvious, or at least from my experience talking to students, it isn't obvious which one's the easy one and which one's the difficult one. So let's take a look. Let's look at problem number one here. Problem number one, job scheduling. Okay, so what's the job scheduling problem? Well, we're going to be given n jobs. And each job is going to have a start time and a finish time. Each job has a start and finish time. And we'll call that maybe SI and FI. So if we're talking about job I, it has start time, SI, and finish time, FI. So that's the problem, but what are we trying to do? What's the goal we're trying to achieve here? Well, we want to find a subset of those jobs, and I'm going to throw in a word here. I'm going to call it a maximal subset. When I say maximal subset, I basically mean the biggest subset possible, or a biggest subset possible. Find a maximal subset of jobs such that no jobs conflict. Such that no jobs conflict. What do I mean when I say conflict? What does it mean if two jobs conflict with each other? Well, we could write down a formal definition of it, and maybe I can leave that as an exercise for you guys. It's not tough, but I don't think conveys the same simplistic, message that a picture does. So oftentimes when we think about the job scheduling problem, you think of it as kind of like a picture like this. We'll have time across the bottom, and I start drawing some jobs. I'm just going to represent jobs with triangles. Rectangles, not triangles. Okay, so this might be job one. And the way that this picture works is this would be the start time of job one, and this would be the finish time of job one. So S1 and F1. And I can draw some more jobs on here. Why not? Maybe we have really long one here. And I'm just kind of making things up as I go. So how many jobs total do we have? 7? Let's label them. 1, 2, 3, 4, 5, 6, 7. And I can put an arbitrary, numbering on this. It seems like I've kind of done some kind of temporal ordering, but nothing strict. And I want to find a maximal subset of these jobs. So what's the maximum size subset of these jobs such that no two jobs conflict? Now, again, the whole point of this was to show what it means for jobs to conflict with each other. Well, I'll tell you right now. You know what? Maybe I'll put in a bonus job here, job 8. Why not? I would say job 2 conflicts with job 1 because they overlap. Okay? Job 4 conflicts with job 1 because it overlaps. Job 3 conflicts with job 2, job 4, and job 1 because they all overlap. They're all overlapping some interval of their time between the start time and the finish time. Job 1 and job 5, they don't conflict with each other because there's no overlap between them. If I were to draw this out, job 1 finishes before job 5 starts. Okay. So what's the largest set of jobs we can find? Well, let's try it. If I take job 8, 4, and you know what, I'll just be clear. That one doesn't conflict with 8 or 6. So first of all, let's just find a subset that doesn't conflict with each other. I'm going to take 1, 6, and 7. So I'm looking at the solution 1, 6, 7. Do any of those jobs conflict with each other? Does 1 conflict with 6? No. Does 6 conflict with 7? No. Does 1 conflict with 7? No. Okay, we're good to go. This subset of jobs does not conflict with any jobs in it. Okay. But is that the largest subset of jobs we could find that don't conflict with each other? Maybe. I mean, let's try some other ones. What about 1, 8, and 7? Do any of those jobs conflict with each other? No, I don't think so, and you can double check for me, but I'm pretty sure they don't. But I mean, it's just as big as this one, so it's not like that solution is any better than the previous one, nor is the previous one any better than it. Well, hold on. What about this solution? What about 2, 4, 8, and 7? Do any of those jobs conflict with each other? No, I don't think they do, actually. Look at that. 2 doesn't conflict with 4, doesn't conflict with 8, doesn't conflict with 7. And what do we have? Well, there's 4 jobs here, therefore we call it a better solution than these, because what are we after? We're after a maximal subset of jobs. And all I care about is, the number of jobs. I don't care about the total interval. I'm not trying to maximize the total, busy time of my processor. I just want the maximum number of jobs completed. This looks like my optimal solution. I'm pretty sure it is, or at least it's a optimal solution to this problem. And it's actually unique for this one, but don't worry about that. We'll get into those details when we go to prove things correct/incorrect. Okay, so that's the job scheduling problem. One thing, hey bud, it's my dog walking by. Doesn't want to be in the video, he's camera shy. Okay, one thing I do want to address here is, what's the complexity of brute forcing this particular problem? Well, I have a set of n jobs, and I'm looking for a maximal subset. So to brute force it, I just check every potential subset of those n jobs, see if they conflict with each other. If they don't conflict with each other, then I have that as my candidate largest one, and I just iterate through every single subset until I find the one that is maximal. Okay. How many potential subsets are there for this particular n jobs? Well, from your discrete math courses, okay, if I have a set of size n, the number of subsets of that set is what? 2 to the n. So brute force complexity is going to be at least 2 to the n. Big omega 2 to the n. So that's a lower bound. So we're going to have to do at least 2 to the power n operations in the worst case. So for those of you that don't know, that's terrible. That's a bad complexity. That's a very, very slow runtime. So brute force is not going to be feasible for this problem. So what would be a potential greedy solution to this problem? Well, we can look at this problem as a series of choices we have to make, and that series of choices is, well, what job do I include next in my schedule? So a greedy solution needs some kind of greedy rule to work off of. And, let's just throw one out there. How about we go with shortest job first, or, choose shortest job. And what would that do? Well, we start to build our solution based off, okay, I'm going to look at my entire job pool here, take the shortest job, and then of my remaining jobs there, I'm going to take the next shortest job that doesn't conflict with my current schedule. So what might that look like? So we'd probably take 2, then maybe 7, then 8, and then 4. Because remember, we're eliminating jobs that conflict with our choice as we move. So that one actually returns an optimal solution. Does that mean that choosing the shortest job first is an optimal solution? No, it isn't. And you should be able to disprove that pretty easily. Anyways, I'm getting ahead of myself. But that would be a potential greedy solution to this one. Choose the shortest job first. Okay. Well, I'm going to put that problem on the back burner just for a moment. Because remember, I told you I was going to introduce 2 problems. The next problem I'm going to introduce is something called load balancing. So what's the load balancing problem? Well, we're going to be given n jobs, similar to this one. But instead of a job having a start and end time, we're just going to have a size associated with the job. So a size might, be a time value like 2 seconds, 5 seconds, 30 milliseconds, some kind of, size. It doesn't necessarily need to be time, but some kind of value that's going to work in our problem setting here. But given n jobs, each with a size, we'll call it SI, why not? So if we're looking at job I, it's going to have size SI. But we're not just given n jobs, we're also given m machines. Okay, so we have m machines, and these machines are going to be homogeneous, so there's going to be no differences between these machines. So that's what we're given. What do we want to do? What's our goal here? Well, we want to find a schedule, and when I say a schedule here, we're going to, send a job to a particular machine. A schedule is, okay, every job has to be accounted for, and I need to assign it to one of my m machines to run. So find a schedule such that the maximum load on any machine is minimized. The maximum load on any machine is minimized. What exactly do we mean by that? Well, let's just look at an example. And we'll look at an example where m equals 2. So we're just dealing with 2 machines. And maybe my set of jobs looks something like, I don't know, again, I'm making it up off the top of my head, which I probably shouldn't do. Let me think about this. You know what? Let's just keep it real simple, just to get the idea across. 1, 2, 3. What do I mean when I say my set of jobs is 1, 2, 3? Well, one of the jobs has size 1, one of the jobs has size 2, one of the jobs has size 3. And again, maybe if it helps you think about time, let's do it. Let's say this job's going to take 1 second to complete, this job's going to take 2 seconds to complete, this job's going to take 3 seconds to complete. Now the way we draw this one, pretty different from that one, is I'm going to have 2 little kind of like open rectangles like this, and this is going to represent my 2 machines. Now let's look at a potential, solution or potential schedule. Well, maybe I throw, and I'll do my best to draw this to scale, the size 2 job on this one. This is machine 1, machine 2, and on machine 2, I throw the other 2 jobs. So I have a size 1 job and my size 3 job here. I was talking about the maximum load before. What do I mean by maximum load? Well, the load on any machine is going to be the total amount of time it requires to complete all jobs assigned to it. So what's the load on machine 1? Well, you just add up all the sizes there. So okay, the load on this machine is 2. The load on this machine is 4. Why? How to get 4? It's just 1 plus 3. Okay, well, I'm trying to find a schedule that minimizes the maximum load. Does this particular schedule minimize the maximum load, or can I do any better than this? I should be able to do a little bit better than that. And I'm sure you guys are way ahead of me on this one. But if I were to instead assign the jobs like this, now this one has a load of 3, this one has a load of 3, so my max load across all the machines is 3, whereas before the max load across all my machines was 4. So this one is a better schedule. And you can kind of see why it's called the load balancing problem, because ideally we want these loads to be as balanced as possible across our machines. In this one, we're able to achieve a perfect balance. That's not always going to be the case. Okay. So what? What might be a greedy algorithm to this particular problem? Well, again, you know, it can get pretty complicated because imagine if you have 1,000,000 jobs to schedule on these machines, try to balance them. It's like, well, if I put this job on this machine here, that might have some implications down the line. Nuh-uh, I don't care about that. I'm talking about greedy algorithms. What might be a greedy algorithm? Well, how about we do something simple like, you know, we don't even need to sort the jobs. We just say, okay, given my jobs, I'm going to have some arbitrary order on them. And when I go to assign the next job, put it to the least currently loaded machine, right? And I just keep continuing until that happens. Is that an optimal solution? No, it's actually not, because let me give you a counter example. It's the exact same one we basically did before. Imagine if I'm given the jobs in this order, just 1, 2, and 3, and I'm doing a greedy algorithm. I say, okay, I'm going to put this size 1 job on the least loaded machine. I mean, they're both not loaded, so you just flip a coin to choose one. Just make an arbitrary choice. Put it here. Then, okay, put that size 2 job on the currently least loaded machine. Well, that's going to go here. And I put the size 3 job on the next currently least loaded machine. I get something like this. Well, that particular greedy solution is suboptimal, but maybe we can do something a little bit more clever. Maybe not. So these are both interesting problems. You know, at the surface, it's not clear how to solve either one of these things, but at least what should be obvious is there at least exists greedy algorithms for each of these problems. They might not be smart, they might not be optimal, but there does exist greedy algorithms to both of these problems. And I forgot to actually address the brute force here. Let's talk about the brute force for just a moment. Over here we had 2 to the n. So what about the brute force on this side? Brute force. Well, let's think about this. For each job, I have one of m choices to make. Think about that. For each job, I can send it to one of m machines. So how many potential schedules exist for this thing? Well, we're going to have something like m to the power n. And if we want to brute force just check all these schedules, we're going to have some kind of big omega m to the power n. Oh boy, that's pretty bad too. We have exponential complexity on both sides. Okay, well remember I told you one of these problems is very, very hard, and one of these problems is actually surprisingly easy. You know, or at least counterintuitively easy. Or maybe it's not counterintuitive, maybe you're a genius and sees a real quick way how to solve one of these problems. But at least on the surface, they seem similar. Brute force is both exponential, and they deal with jobs and sizes, and they're at least related problems, at least somewhat similar problems. And I want to give you guys 3 choices. And we're going to try to order difficulty of these problems in some way. And I haven't really given you a formal definition of what it means for one problem to be more difficult than another. But, in some sense, as human beings, we have an idea of, what's a hard problem to solve, what's an easy problem to solve. And, I'm not looking for anything super formal here. I'm just, looking for you to kind of gauge your intuition. But we're going to have job scheduling. We're going to have load balancing. And we're going to have load balancing with m equal to 2. What does that mean? That means we're going to have exactly 2 machines instead of potentially 3, 4, 1 billion machines. Those are my 3 candidates. And I'm going to have some kind of spectrum here. Over here, we're going to have easy problems. Over here, hard. And I want to have some kind of ordering. Now, there should be 2 problems that, are easy to order, kind of relatively right off the bat here. And I think it's a strong argument to say, look, with m equal to 2, that's going to be an easier problem to solve than load balancing with general M, right? With general M, there could be 100 machines, 1,000 machines, 1 billion machines. Well, it's probably going to be easier to cope with if, in general, if M equals 2. Okay, so I'm going to say load balancing with M equals 2 is here, and load balancing is here. All I'm saying is load balancing is harder than load balancing with a constrained small number of machines. Okay. Well, where does job scheduling go? That's the only one we still have to put. Is it easier to solve than both of these things? Is it somewhere in between? Or is it harder to solve than both of these things? And I want you to just ponder that just for a moment. And again, I'm not looking for any great insight here, or some kind of groundbreaking like, wow, I can't believe they're able to see that. But just, honestly gauge what your intuition is telling you. And maybe pause the video, because I'm going to talk about where it actually goes in just a moment. So I'll give you, pause it now. 3, 2, 1. Okay, let me tell you where it is. And before I do that, I usually ask this question to my actual, in-class lectures back before, we weren't allowed to see each other. But it would usually, the answer that the class gave, 80% of the class came to the conclusion that job scheduling is harder than both versions of load balancing. And, maybe if you came to that conclusion too, you can write in the comments down below why you came to that conclusion. I find that fascinating. And, I've talked to students before and I still really haven't got a clear answer to why a lot of them think that's the case just based off their intuition. But as it turns out, job scheduling is actually easier than both of these problems. And when I say it's easier, what I really should say is it's way easier. So I'll try to get that as close to easy as possible. So job scheduling is way, way, way easier to solve than load balancing, even when load balancing has a small number of machines, just 2 machines. Why? Well, what do I mean when I say it's easier? Well, we're talking about greedy algorithms. Job scheduling has a greedy algorithm that solves it, an optimal greedy algorithm. That means there exists a greedy algorithm such that for any instance of this problem, any configuration of an arbitrary number of jobs, it will always find a maximal subset of those jobs such that those jobs don't conflict. And not only does it do that, I'm going to spoil this a little bit, check to see if you've actually watched the videos to the end here, but the greedy solution to this one runs in n log n time. And if it's sorted ahead of time, it actually runs in linear time. So there's a very, very fast, simple algorithm, greedy algorithm in fact, to solve this problem. Wow. So if you don't have a lot of experience with these sort of problems, this is actually pretty shocking because it seems like a hard problem. And some of you maybe even came to the conclusion that's a hard problem. My, upper year, third, fourth year computer science students at University of Toronto actually usually think it's a pretty hard problem when they first see it. Turns out it has a very, very simple solution. Over on this side, and this is getting outside the scope of this course, load balancing is what we call an NP complete problem. So it's a special class of problem where the best, the most efficient algorithms we know, the smartest minds in the world know right now to solve this problem don't beat brute force. It's still big omega m to the n. The best known algorithms we have to solve this problem runs in exponential time. We have not figured out how to do any better than that. That doesn't mean that there doesn't exist one that's better than that. We just don't know about it if there is. In fact, if you were to find a solution to the load balancing problem that ran in n log n, you'd solve one of the most important open problems in computer science right now, which is the P equals NP problem. And it's one of those problems where you get $1 million if you solve it, plus a lot more than that probably. So this is a very, very hard problem. This is, I'm not going to say a very, very easy problem, but it's relatively very, very easy compared to this one. So we're going to see, okay, Vince has told me that there's a greedy algorithm which solves this. But what is it? Is it shortest job first? Is it something crazy like longest job first? Is it something else? Well, we'll take a look at potential candidates next time, prove some of them incorrect, and then maybe get started on proving the correct one actually correct. Okay? Thank you very much for your attention. See you in the next video.